Thank you. It has been a long 5 years, lots of stuff going on in between. Last night as I was looking at this talk, I reflected that after 5 years, I should have condensed my title a little bit. But I'm going to tell you what I'm going to talk to you about today, and that's thinking about coastal areas from the perspective of the environment, and namely the interface of land and water. So if we're talking about living with water, that edge is critically important. We know in a lot of places tide rises and falls, whether it's due to the moon or due to the wind. We've talked about sea level rise already. We've had increased times of heavy precipitation. So the way that we connect with water at that interface is critically important for the environment, but also just critically important for how we live. And one of those things is through rice and growing rice. So these different factors that affect that margin are critically important. And what my lab, this is our little logo thing that looks Edward Gorey-esque, you'll probably notice if you know Edward Gorey, we're really interested in the biological, chemical, and physical processes at these margins. On the right-hand side, I have a very not beautiful map from Google Maps of this area. And it's just to ground the things I'm going to talk about here. I'll end up at the end of my talk focusing in directly on Georgetown and thinking about the habitats that are here, the values that they provide, how things were in the past perhaps and may change as we go into the future. But for me, it's a very place-specific thing. This map intentionally includes Brook Green Gardens, one of my favorite places growing up. Often went with Jim. Afterwards, we would usually go to the fireworks store. And that was a great joy that my parents weren't necessarily that crazy about. So thank you to Jim for being my fireworks enabler. And also one of my favorite papers, it was a project we did at Brook Green Gardens. One of my intrepid colleagues trucked salt water up to Brook Green. It's in an area called the tidal freshwater zone, where the water rises and falls, but there's no salinity. And from a biological standpoint, it's a remarkable place. It's also a really important place for all the things that we study, the processing of nutrients, the fixation of carbon through photosynthesis, and all of these things underpin a lot of our quality of lives. And that's what I'm going to talk a lot about today, is this concept of ecosystem services, which was first really into the mainstream about 15 years ago and has really become important to us because the things we do were not necessarily that easy to connect to people's everyday life. But as you get a system to understand the natural ecosystems as a value for people, it just makes it more accessible. We don't want to monetize the environment. We just want people to understand the things that we care about and the things we understand to be of value in a way that is meaningful to them. And the most common way is just to assign a dollar value. So as we think about ecosystem services, there's a lot to read here that can be pretty dense. But if you think into the parsing of the types of services that ecosystems provide, these provisioning services, so that's like energy, talking about peat, people extract peat and use that for energy. Seafood, certainly very familiar with that here. All of the things related to transportation and national defense are becoming more and more prominent as we put people in places where they haven't historically lived. So two things are happening. The water levels, that particularly at the landwater margin, are changing and changing more quickly and more extremely. But you're also putting more and more people, and I don't have to tell you because everybody wants to live here, just like everybody wants to live in all the beautiful coastal places. You have more of a connection between people and these potential risks. So these services become even more valuable. So we've got regulating services like flood prevention. Certainly if you've ever been at the edge of a marsh as water flows across it, it's a very different thing than water flowing across a parking lot. So it's often these ecosystem services, I think, are perhaps a little bit overblown. People think about, oh, salt marsh restoration is going to save the world, or something like a living shoreline or other green infrastructure is an amazing thing that's going to solve all our problems. Our perspective is they're great, but we really want to know exactly what they do. So if you think about flood mitigation, if you have a marsh that's this high and you have 20 feet of water, they're not really going to interact that much. So just being realistic about what these services are is a big part of what we do. And then finally, and really importantly, are cultural services. So these are harder to quantify. These include spiritual, heritage, recreational is a little easier to quantify, educational. So these are all important areas where natural systems provide quantifiable dollar values to people. And of course, we don't ever, one of our kids, as I was doing this work 15 years ago when they were in school, in their low grade school, asked when I was gonna get a check for all of these ecosystem services. Who's gonna pay us for them? Well, no one's gonna get the money, but if you don't have the systems to provide you these services, you're gonna have to pay for something else to get them. So we think a lot about nitrogen cycling, which I'll talk about in a second. If you don't have this natural nitrogen removal, you're gonna have to pay for it in another way, whether it be through sewage treatment or stormwater management, something like that. So thinking more specifically about coastal systems and the services they provide, shoreline protection is an important one. I already talked about trying to bound that and be realistic. A marsh can baffle wave energy and can damp waves, but it's not going to stop a hurricane. Nutrient cycling, the area I'm going to talk as an example of all these services about today that we work a lot in, is critical. It balances our nutrient cycles so that we don't have excesses that create problems like algal blooms that are throughout coastal areas and are a product of something that I'll talk about in a second, which is actually a good thing. Erosion control, we've already talked about it. If you have a marsh on the edge of a scarp, it's less likely to erode, full stop. Will it erode some? Quite possibly. But there's a lot of value to be had from whether it be oyster reefs or mangroves or salt marshes in controlling erosion. Water purification, again, the idea of the processes that go on, and then also just the physical slowing down of the water that draws materials out of the water column and puts in the sediments. Carbon sequestration, a little bit of discussion this morning already. These are places where you have a lot of primary production. Probably have heard of blue carbon, this idea that the fringe of the coast and the ocean together are a significant sink of carbon. Really important, again, something where we're working hard to quantify it, to develop the data we need to say exactly how and exactly how much, because this is an area where there's been a little bit of euphoria also. And then finally, and really importantly, fisheries. In North Carolina, we have a nonprofit whose logo or whose motto is no wetlands, no seafood. A little oversimplified, but not that far from the truth. These natural systems are what make these areas so great for all sorts of fishing. So this is a table from a paper that I was part of that was looking at oyster reefs and ecosystem services. And interestingly, what it did was look at the world's major habitats in coastal areas. So salt marsh, seagrass, mangrove, coral reef, and oyster reef. Look at the area that's been restored, so this is in hectares, and then how much does that cost? This is in thousands of dollars per hectare, and then the percent global loss. So there's a lot here. But I'll offer this as a take-home. We haven't restored a lot of oyster reefs. We've restored more than we had in 2012 when this was written, but it's very expensive and it's very hard. We've restored a whole lot more salt marsh. Probably because it's somewhat cheaper, that's certainly one of the things, but also because it is in a place where the opportunity presents itself a little more easily. Thinking about South Carolina coast, thinking about this area in particular, the history of rice. When you think about land modification, people generally in coastal areas think of it as one-way street. But with rice culture, it can go back. And so that's a really interesting dynamic in terms of restoration, conservation, and sustaining habitats going forward. But then just looking at the global loss, it's pretty staggering. About 90% of the globe's oyster reefs have been lost. Up to 80% of salt marshes, about 50% in North Carolina, a little bit less in South Carolina. Seagrass, numbers vary, but still quite high everywhere. And then the more tropical, the mangroves and oyster reefs, also quite high. Coral reefs, I think 20 is considerably higher now than it was in 2012. So all this to say, if we believe the premise that these habitats offer us value, and we know we can quantify it, and I'll offer you some numbers in a minute for oyster reefs, we've lost a lot. We know it's really expensive to restore them, and we really haven't made as much headway as we should in our restoration. So why is all of that? And I think I've begun to talk about it a little bit. It's complicated, it's expensive, there's uncertainty related. You're in a really dynamic environment, so a storm can wipe out all your efforts the next year. But it's important to think about these costs and the opportunity that restoration offers in the context of conservation. So not losing these habitats. And that's why we have the regulations that we do. Some of them, if you happen to be familiar with the Waters of the US designation that we just changed in the United States, that left a whole bunch of wetlands that used to be protected unprotected. So we expect to see some of these numbers ticking up, because of the nature of the regulatory environment. So I'll wrap it up by saying we've lost a lot of habitat. We're fortunate, you all are fortunate, and I'm fortunate to be in a place that has a lot of the habitat remaining, which is so great for so many reasons. But in order to get back, to restore, it's going to cost us a lot of money, and history would suggest that it's pretty hard to do. So the fundamental premise of our group's work is that there's too much nitrogen in the environment, and no one can argue with that. But the reason it's there is because we fed the world's population. So after World War II, we commercialized the Haber-Bosch process, which allowed us to take the 70-some% of nitrogen that's in the atmosphere and fix it into nitrogen that can be used as fertilizer, which is a revolution. It's amazing. We were so great at it that this problem occurred along with it. As population grew, as we did more intensive agriculture, as we applied more of this fertilizer that miraculously could be brought from the air, which is remarkable, we got to a situation where there was more nitrogen than the environment could accommodate. Nitrogen is the backbone of proteins and amino acids. It's critical to all human life. It is critical to all of nature, and it is the element that generally limits primary productivity, so plants' growth, at the coast. Particularly in aquatic systems, upland, in freshwater, you think about phosphorus being the limiting nutrient. As you get to the coast, it tends to be nitrogen. So when you have too much of the limiting thing, you're going to have a problem. Very quickly, we're going to look at the nitrogen cycle, not very long. But I think it's really important to ground some of the things we're going to talk about going forward. On the left-hand side, you see this process, denitrification. It takes biologically available nitrogen and converts it back into N2 gas. It's putting the genie back in the bottle with the stuff that we've fixed through Haber-Bosch, whether it be in agriculture, fertilizing your lawn, sewage treatment. You have lots of fixed nitrogen coming into the environment. That process can remove it. And that's been the better part of the work that my group has done for the past 20 years, is trying to understand how coastal habitats process nitrogen, specifically do this process. This cycle there's a great depiction. It's a little simplified. There have been some more processes that people have identified and have found, but this one is nice to me because it looks balanced. And I've already alluded to the imbalance comes from additional fixed nitrogen coming in on the right-hand side. So more nitrate, more ammonium, the forms of nitrogen that plants take up through fertilizer, then the system can accommodate. So if you put that much nitrogen in a pond, you're going to have more algae than the zooplankton can eat, and more zooplankton than the fish can eat. And so the original carbon is going to accumulate and be pollution instead of being the base of the food web. And that's what we're trying to find, is that balance again. So in 2011, our group was out in the field in North Carolina, and we were working on salt marshes and seagrass beds. And we looked at an oyster reef and decided that we would take samples the way we do there. We take sediment cores, take them back to the lab, run them through a machine called a membrane inlet mass spectrometer, and we get rates of this process. This process is hard to measure. So we took cores from the oyster reef, just thinking, well, we'll figure out what's going on here and look it up in literature when we get back. When we looked it up in literature, no one had ever done it before, so that was pretty exciting. So we hustled and published this paper comparing nitrogen removal from these natural environments, salt marshes, oyster reefs, seagrass beds, intertidal flats, so flats where the water rises and falls, and subtidal flats. And what we found was really interesting. Nitrogen cycling in oyster reefs was really important, but it was important across the habitats, and we did it on a seasonal scale. And so this coincided with the advent of the ecosystem services era. So for us, it was a magic time because this figure in and of itself is not terrifically compelling, except for the color scheme that I fought for, and lots of people in my lab did not want. But what makes it compelling, I think, is that all of these can now be assigned dollar values and meaningful connections to people's activities and mitigating impacts of people's activities. So how can we live better at the coast is our big challenge. So following this work, well, the first thing we did was spatialize it. So go ahead and multiply everything by the area of the habitat, figure out what the total nitrogen removal is, and then figure out that within our little Ogue Sound, little small sound, this is providing more than $1 million a year in free nitrogen removal. And that's the kind of thing that gets people's attentions. If you say salt marshes are awesome, probably this whole room is gonna agree with me, but lots of other people are gonna just shake their head or not care. But if you tell someone that you're getting $1 million free, it makes people consider, okay, and what does that have to do with how I behave going forward? And so, interestingly, subtidal flat, tons of nitrogen removal, because there's so much of it. Even though the highest rates are in oyster reefs, the total amount in oyster reefs was a little bit lower. But we wanted to know why, and we wanted to know, is this going to scale? So I'm gonna walk through a series of summary slides from papers that we published specifically on oyster reefs, because the oysters were the most compelling. People have been working on salt marshes for a long time. We really wanted to dig into the oyster reefs. So we did, and as anyone who's been there knows, they're formidable. They're very sharp. They're hard places to work, but absolutely delightful and interesting. So, back to the table that I showed you about habitat loss. This is a figure from that same table, and this is the ecosystem services of oyster reefs. So they are worth, to people, $10,122 per hectare, and that was in 2012, so it's probably a bit more now. So we broke that out, and I can't tell how little that is. Yeah, that's not too bad. We broke it, the pie chart shows you how this value is distributed. So whether it be through shoreline stabilization, through facilitation of SAV growth. When oyster reefs are there, they baffle the waves a little bit and collect some of the sediment and allow the seagrass to grow a little bit better. Nitrogen removal that I've already talked about, and then also commercial fish, so as a habitat for commercial fish. I will not lie and tell you that we were not excited that nitrogen removal was a huge proportion of the total value of oyster reefs. And what that did was create a whole new way to restore oyster reefs, because we had quantified what you're going to get every year in dollars from a hectare of oyster reefs, and that can help. That return on investment, though you're not going to get handed the cash, was important to the decision making. We wanted to understand, how did the oyster's context within the environment work? This was a time, and it's still a little bit true now, that people were euphoric about oysters, and they thought oysters in the environment were going to solve all of our environmental challenges, and they're going to solve a bunch. But there are a lot of things that matter a lot about how they work, and one of them is where they are in the landscape context. So in this experiment, we were fortunate to have had a colleague who built a bunch of oyster reefs on mudflats, adjacent to marshes, and then adjacent to both seagrass and marsh. So the idea here is, what is the value of this reef in these different contexts? Is there an additive value if it's adjacent to another habitat that does something sort of the same? Or is it just oysters are good everywhere? And what we found was not quite what we would have expected, but a modified version of that. So this is the process, again, denitrification, so nitrogen removal by the sediments. We have the left-hand two bars in both the mudflat context, so that's just a flat, the marsh, and the seagrass are the measurements of denitrification with and without oysters present. And then the right-hand side bar is, no, forgive me, the first two bars are the control, so just the site, and then adding nitrogen, and then the right-hand bar is with oysters present, so mudflat and that's with oysters, so mudflat with oysters, and then the right hand of those two bars is a nitrogen pulse. So what we found was that the ecosystem service only has value if it performs when there's a lot of nitrogen there. So when there was a lot of nitrogen, and if you had oysters, they denitrified a lot. So that was, again, if you're going to evaluate it in dollar value to people, it's a critical step to have it be under conditions that are important to people, so nutrient-enriched times. We also wanted to know when they start bringing value and why. So we built a bunch of oyster reefs with live oysters and a bunch with just oyster shell. And what we found was that the shell alone enhanced this process of denitrification a little bit, but it's really the live oysters that did the trick. There's a whole bunch of theory about ecological engineers, ecosystem engineers. These are organisms that modify their environment both through their activity and through their structure. And this was a kind of classic example where the living oyster that also had its structure up in the water was the important thing. Finally and importantly, we needed to know if you added more oysters, were you going to get more denitrification? Again, people find something that works and they tend to want to do even more of it. And this was pretty good evidence that you could go to a pretty high density of oysters and really end up with more and more denitrification. So Where should you do it? How is it changing? Is it related to the oyster's activity or just their structure? And then how much can you do and still get this return? Really important things from our perspective in thinking about that ecosystem service. Finally, this idea of living shorelines, again, something that's really received a lot of attention, lots of federal funding. We wanted to know how people talked about living shorelines and water quality, but there were no data. And this was a study we did looking at oyster reefs of different ages and marshes of different ages through time, and again, measuring this process that we're so interested in, denitrification, and finding that in fact, they do provide a great service of nitrogen removal, and they do it pretty quickly, which is good. Salt marsh restoration, it's a long time been thought that you need up to 30 years for the marsh to mature in order to be able to get the services you expect. So when we think about oyster reefs, this is what we hope to think about, but the reality is when we think about habitats, we're often thinking about the fringes here in Georgetown. We're thinking about areas that are adjacent to urban and potentially growing developed areas. And one place where we've worked a lot, if you squint your eyes, you can maybe convince yourself it's Georgetown, the water's a little too big, but this is New Bern, North Carolina. And so 2 rivers on either side, the Neuse River going down, which tends to have flooding coming up from the coast. Also the Trent River, which has river flooding. So kind of a similar context. So my student Ann Smiley, who just had a baby 2 days ago, which is very exciting, did a ton of work in New Bern. And what she did was look at not only the habitats we work on, but looked at the habitats that occur in urban areas. So she was really interested in, as these areas flood, how are things like lawns gonna behave with respect to the factors that we're interested in, the nitrogen cycling idea. So she quantified the area of habitats, did the same flux measurements I talked about we do in a lot of places. But an additional angle she took, and we talked a bit about storms already today also, is she looked at all the storms that had occurred in the recent past in New Bern, and it was a lot, and was able to get the flood footprint of each of the storms to outline the watershed, the area of land that drains to that river or stream, and then spatialize the nutrient cycling measurements that we make to the floodplain. And again, so this is like, ecosystem service is great in principle, but in practice, if you're not getting it in big times like hurricanes, what value does it really have? And it was really exciting to find that these habitats perform really well during hurricanes. It was less exciting to really reckon with the fact that the frequency was growing, the flooding area was growing, the area flooded that was directly connected to people was growing really radically. So certainly challenges remain, but from this water quality regulating perspective, Ann's work showed that urban areas like New Bern, and I think it would translate almost directly to places like Georgetown, are in pretty good shape because they have a lot of remaining habitats. So turning back to Georgetown, and you can see the marsh in the background, I think there, and trying to think about, so going back to my too long title, thinking about the past, present, and future. It's a historic, wonderful place with great old maps that show us what used to be, with lots of great marine efforts going on in the area. The map on the right comes from Brook and is a land use map, so the red areas are where people are living, but the rest of them are natural systems. So there are an amazing array of natural systems. They have in the past, whether it be through rice cultivation or whether it be through places that people were able to have commerce with the rivers, they've been of huge value to people. And that value has changed as we move to a time when we don't need necessarily the absolute fundamental services that they provide, but things like fishing remain a critical part of the economy, whether it be directly through providing fish as a protein or whether it be through an attraction for tourism. So without question, Georgetown benefits from its ecosystems and its ecosystem services. We try to find data to look at the past, the present, and to the extent we can to speculate about the future. This is looking at a time step, shoot, now I forget, I think it goes to 2016, I think it's maybe 2006, I think it's a 20-year time step. And the green areas are, the dark green areas are forested wetland, the light green areas are salt marsh, and the red are areas that indicate loss. So these are satellite data, and you would have to look at each of the individual, particularly the big red blocks. I bet people are looking at them and know exactly what happened. But it's important to keep taking stock and to understand where your assets are. And as we talked about all the different types of ecosystem services, if there's some that are particularly valuable, perhaps emphasize a management strategy that sustains the ones that you know have the most value. So one thing we try to do is find as much data as we can in the past. For oyster reefs, it's often very hard. Salt marshes, there tends to be a little bit more. And we want to think about all these things in terms of the major changes that are going on. So clearly development is a huge change. Sea level rise is a huge change. Storminess is a huge change. These are things that are all very likely on the uptick at some at higher rates than others. Some we can control, some we can't. So this is a figure that, I'm gonna pause it in just a second so you can see it from the beginning. Where's the little pause button? All right, I may not have that control, but that's okay. So that is a half meter of sea level, or I'm sorry, a half foot of sea level rise. So the first is 6 inches of sea level rise, and the final here is 3 feet of sea level rise. And I think it's a really interesting animation. It shows you probably a lot about the topography, because what happens with sea level rise is as you get to a certain point, if water level has risen above the top of a marsh, it will be inundated and it'll be lost. So this is a projection for the numbers are on the left-hand side. Across the x-axis, you have from 0 to 3 feet of sea level rise, and up top you have, I think this is, area lost. So you could see as you get to a meter of sea level rise, whenever that happens, there's going to be significant marsh loss. Interestingly, green here is marsh gain, and what that is upland areas that get covered with water and can convert into salt marshes. This is from a NOAA calculator that puts together all the factors that they could come up with that they think would predict marsh loss well. It is not perfect, and it'll be much more dynamic than this. But I think this does a really nice job of suggesting, who knows exactly when 3 feet of sea level rise will occur. In a storm, it could occur tomorrow, but for a sustained period of time as a new water level, we're some time out. But these are the places we're gonna have to think about. And as Don alluded to, these are places also they're gonna have more salt, because we're gonna have more water coming from the ocean end member. So going back to this idea of ecosystem services and thinking forward, we know development is changing things. I talked about the waters of the US, a specific policy that's remove protection for a whole class of wetlands. There are a lot of decisions, local decisions made on one-offs on permitting that can have huge impacts. So that combined with sea level rise, combined with storminess, is likely to change our coastal landscape, and probably in a way that's gonna have less habitat, less natural habitat than it does now. So as we look forward and think about the water quality challenges we're facing, the flooding challenges we're facing, standing water like sunny day flooding, not even related to big storms, what of these services do we really want to value, and how can we make that happen with a smart approach to habitat management? And I think in our group, we think a lot about nitrogen cycling, but we also think broadly about the whole suite of things that these habitats do. And we believe, and I hope I've convinced you, that there's some value to really understanding why and how these systems work, and not just saying they work and that's great. And that's the kinds of stuff that we like to do, and we love to think about new systems, and it's been a lot of fun to think about a place I love so much. Thank you all for coming. I'll just quickly, full credit to my team, and the middle picture, I just told them we wanted to look like we were a folk band. And so that's my second favorite picture. The one where we wanted to be in a Quentin Tarantino movie was a little funnier, but this one is a good one. So I've had amazing grad students who've done amazing work, and it's been very gratifying. And thank you all for listening, and I'd be happy to answer any questions. So there's some atmospheric deposition, which is a known quantity per area, and that varies depending where you are. Like if you're just downstream or just down in the airshed from Tennessee Valley Authority, it's more. There'll be some here, but not tons. There's some groundwater nitrogen that comes in, but the principal delivery is from rivers the freshwater end member, bringing it in from the big watershed and having it get down to the salty end.
So mostly from agricultural?
Agriculture, yeah, certainly sewage treatment is a big one. We've gotten a little bit better at sewage treatment, but there's still an awful lot of less effective systems out there. Certainly fertilizer at the scale of people's yards can be non-trivial. Concentrated animal operations can be big sources depending on where they are and how well they're managed. So that's a good question. And on the scale of the reef itself, there's great documentation that those efforts, when they take hold, are great and they can have a natural-ish marsh or a natural-ish oyster reef pretty soon. So I would say we have the technology to do it well on a smaller scale. At the scale of like an estuary, I think it's harder to know how much of that you would have to do before you really had a system-wide impact. So if, say you had an algal bloom problem in a big bay, doing oyster castles to the point where you would mitigate that bloom, I don't think people have done that yet. But to your point, I think it's just a giant effort, and that's complicated work for sure. Yeah, 100%. And our work indicates that oysters are the very best investment in terms of nutrient cycling, even if you go back to how expensive they are to restore. Yes? So it's worse for seagrass. Seagrass, it's really bad, particularly in Florida, so much so that making a prop scar is now a really significant fine, like tens of thousands of dollars. Oyster reefs are pretty robust. If you drive your little skiff over an oyster reef, the reef will be a little sorry, but you might be more sorry. So the bigger problems are disease and fishing. Those are the big competing ones. And this idea for us, we've always worked on things like on plants that people don't have tons of affinity for. So it's been weird to go into an area where people really want to eat them. And so this balance of, are you going to eat these oysters, or are you going to let them do what they do in the environment? And we've tried to find a both solution there. There's some ways you can harvest that are less destructive that allow those services to continue. But the big ones, people point to general water quality degradation. So if you have pathogens, you can't eat them. That one's interesting because if you have pathogens, they grow beautifully because nobody eats them. So some of the hardiest oyster reefs are just downstream of sewage treatment plants. So that's one that we've looked at as well. And we wanted to restore them downstream of sewage treatment plants, but we were told no, because that's an attractive nuisance. You'd be putting in something that people could plausibly eat in an area where they absolutely should not eat it. So that was tough to deal with, but I'd like to think people are smarter, but we still have the little don't drink the toilet water if it's harvested from the roof. So yeah, not so much with the small crafts, but there are lots of challenges that oysters face, principally disease. And disease is changing as water level rises and the salinity regime changes. So there are different prevalences, and there's different challenges related to disease depending on where you are in the salinity regime. So oil, not maybe in volume, absolutely, but just in the background, not quite as much. A lot of oil from small boats is pretty similar to short-chain hydrocarbons that organisms see all the time. Weirdly, my dissertation research was on degrading oil in marinas using natural systems. So it's stuff that can be chewed up, and there's less toxicity, enduring toxicity than you would think. The volatile stuff tends to go right off. That's absolutely right. So there's a paper that I'm a part of that's called Engineering Away Our Natural Defenses. And so it's about hardening shorelines and losing the habitat seaward of them. Almost never do they work well together if water level's rising. Because as water level rises, you're going to get waves hitting whatever the hardened structure is. If it's a shear thing, it's going to bounce right back. If it's like riprap or something like that, it'll dissipate it a little bit. but almost always you're going to lose that habitat in front. And so that was the genesis of the idea of living shorelines. I have to use air quotes because often they have like granite, which is not living and often not native, but sort of solutions that involve green elements. And so you would put in, your hardening would be in a sill a little bit offshore, and behind it you would put a salt marsh and an oyster reef. And there is potential for those things to work. Like a lot of things I've talked about today, their popularity and the enthusiasm for them far got ahead of our information about how they might work. And so you can imagine wanting to be really careful about putting big granite rocks out there, not knowing how they're going to behave in a big storm. But to your point, there is a constant tension between shoreline hardening and the natural system.
All right, any other questions or comments, observations? Thank you, Michael.
Thank you.